Okay, in this video, we're going to look at the laws of logarithms. Now, the laws of logarithms are heavily related to the laws of exponents. And let's look at a theorem about the laws of logarithms. So if your base b is greater than 1, then the function log base b of x is going to be a continuous one-to-one function. And its domain is going to go from 0 to positive infinity. And its range is going to go from negative infinity to positive infinity. Okay. So if you have two numbers, x and y, these guys are both greater than 0, and r is any real number, then we're going to have three laws of logarithms. And before I tell you what these laws of logarithms are, I want to remind you of the laws of exponents. So let's say that that number x that they gave us was equal to the base b to some power m. And let's say that the number y was b to some power n. Then how did the product rule work? Well, if you took b to the m times b to the n, what we saw earlier is you simply add the exponents. You'd get b to the m plus n. Okay, so now let's take a look at the corresponding law of logarithm. If we took the logarithm with respect to the base b of these numbers x times y, we're going to get that's equal to log base b of x plus log base b of y. Why does this make sense? Well, remember, logarithms are really exponents. So if I look at what's log of x times y, log of x times y, here I have x times y on the left side. And when I want to look at the power of that product, what this is saying is I can simply add the exponents for the x guy and the exponents for the y guy. So I simply add the b and the n together. All right. Let's take a look at the second law. The second law involves the quotient. So remember, if you had b to the m divided by b to the n, that's going to be equal to b to the m minus n, like that. And this is really, x divided by y. And the previous one was x times y, right? So when we write down the quotient law of logarithms, we're going to get log of base b of x divided by y. That's really what the left-hand side of the equation is. Looking at those exponents, what's the resulting exponent going to be? The resulting exponent is going to be the log with respect to base b of x minus the log with respect to base b of y. So we're just going to subtract the two exponents. In the final law of logarithms that we had something like x to the r power. And how is that expressed? That's really b to the m raised to the n power, raised to the r power, sorry. And that's going to be just equal to b to the m times r. Right, so how do we express that as a logarithm law? Well, if you have log base b of x to the r power, what this really says is you can bring this power here down in front and multiply. So that's going to become r times log base b of x. Now remember, this log base b of x was just m. So really we got r times m. Okay, so these are the three laws of logarithms. And why don't we use these laws of logarithms to look at a couple of examples? So let me look at these examples right here. Okay, so the first thing when we look at we want to evaluate log base 4 of 2 plus log base 4 of 32. So here I have a sum of two logs. That means it looks like we're probably going to use this first law of logarithms involving the product. So this is going to be equal to log base 4 of really 2 times 32. And 2 times 32, the last time I checked, that was equal to 64, right? So this is going to, we can call this, whatever this exponent is, we can call that equal to y. So I have this equation in logarithmic form. And what I want to do in order to figure out what y is going to be is I want to rewrite this in exponential form. So when I write this in exponential form, the x value is 64, the base is 4, and the exponent is y. Okay. Now the next thing I want to do is I want to write both sides of that equation with respect to the same base. So we know that 64 is really 4 to the third power, and the right-hand side is still 4 to the y-th power. And then this tells us because 4 to the x is a 1-to-1 function, the exponents must be equal to each other. So this tells us that y is equal to 3. And that's going to be our answer for the first part of the example. Let's take a look at the second example over here. The second example involves a difference of two logs. So that's going to be a quotient rule. So I can write this as y is equal to log base 2 of 80 divided by 5. And 80 divided by 5 is 16. So we can write this as log base 2 of 16. And this is our equation in logarithmic form. So I want to convert this to exponential form. When I do that, I'm going to get that the x value of 16 is equal to 2 to the y-th power. Remember, logarithms are exponents. Next, I want to rewrite this as two numbers with the same base. So 16 is 2 to the 4th power, and the right-hand side is still 2 to the y-th power. And again, because 2 to the x is a 1-to-1 function, that means when the output values are the same, the input values, y and 4, must also be equal. So we get our final answer is y is equal to 4. Let's take a look at our last example, example 2. For example 2, we have the limit as x goes to 0 of log of sine squared x. So I think I can rewrite this a little bit. I can rewrite this as the limit as x goes to 0 log of sine of x squared, like this. Now, when we write it like this, you might be very tempted to take this 2 and bring this 2 down in front. I mean, obviously, I taught you the 3 laws of logarithms, so you're thinking, man, I would love to bring this 2 down here like this. And in this case, we cannot do that. Why can we not do that? Let's go back and look at our theorem. In our theorem, we really required that both x and y were greater than 0. And if we go back and look at our function over here, we can see that this guy involves sine of x. So let me just draw a quick sketch of sine of x for you. So sine of x looks something like this. Here's 0, here's pi over 2, here's pi, here's negative pi over 2, here's negative pi, here's 1, here's negative 1. This is just a sketch, it's not to scale, right? And if I go to graph this guy, it passes through 0, comes up to 1, goes down to pi. So this part looks like this, like that. And on the left side, it drops down to -1 and goes back to 0. So this part looks like this. This is one period of sine, right? And what do you notice? You notice that we're taking our limit as x goes to 0. So if I come from the right side like this, clearly this is going to give you a positive number coming from the right. But if you come from the left side, when you come from the left side, this is going to give you a value less than 0. So I don't want to allow a value of less than 0 because that's outside the domain of the logarithm. Remember, the graph of the logarithm looks like this. The graph of the log looks like this. It passes through the point 1, 0, and it has a vertical asymptote here of x equal to 0. So our logarithm looks something like this. So it's not defined for negative values of x. That's why we had this restriction up here involving x and y both having to be greater than 0. Okay, so this is a long discussion, but the point of this is we are not allowed to bring down the 2 because when we bring down the 2, that's going to make these numbers over here negative. And I want to keep that squared there to keep everything on the inside of the logarithm positive. So for this example, I cannot use the third law of logarithms because it's going to violate the idea that everything inside the logarithm has to be positive. I need to keep that square there. So to solve this problem, I am actually going to approach from the left side and approach from the right side. So let's take the limit as x goes to 0 from the positive side. That's going to give you log of sine of x squared. So to make it more obvious, I'll put that whole parentheses around that whole thing. So what's happening here is that we're plugging in numbers and they're getting closer and closer to 0. When you square them, it still gets closer and closer to 0. As you approach, you look at the logarithm graph, the green graph, as you get closer and closer to 0 from the positive side, you're going to go to negative infinity. So when we come from the right, this is equal to negative infinity. What happens when I come from the left? I take the limit as x approaches 0 from the left side of the log of sine of x quantity squared. And what's happening with this guy is, yes, I'm coming in from this side of the, I'm coming from the left side of 0. So at first, my sine of x values are going to be negative. But remember, I still have that squared there. Squaring a negative number makes it positive. So really, instead of approaching 0 from the bottom, because I'm squaring it, actually, I'm plugging in very small positive values of sine of x squared. So these guys on the inside are going to be very small positive numbers. Very small positive numbers essentially means we're coming from the right side of 0 again. So because we're coming from the right side of 0 again, this limit is going to go to negative infinity as well. So you come from the right, you get negative infinity. You come from the left, you get negative infinity. Therefore, the limit as x approaches 0 of log of sine of squared x, this whole thing right here is going to be negative infinity. And I've got to highlight this because that's our final answer. All right, this example is not super straightforward, but it's I think it's a good discussion to go over when you can use the law of logarithms and when you cannot use the law of logarithms. All right, everybody, take care.